In this exercise, we will show how one can determine the volume of the region above the xy plane, and that is inside both the paraboloids z equals 4 minus x squared minus y squared, and z equals 4 minus x squared minus the square of y minus 3. The first paraboloid, z equals 4 minus x squared minus y squared, has the z-axis as its central axis. By translating the first paraboloid and its axis 3 units along the positive y-axis, we get the second paraboloid and its central axis. Since one paraboloid is a mere translation of the other, the curve of intersection between the two paraboloids is equidistant to the central axes of the two paraboloids. Let us refer to the region whose volume we are going to find as the solid. The solid's farthest extent from the origin along the y-axis is inside the second paraboloid and is part of the intersection or trace between the first paraboloid and the xy plane. Since z is 0 on the xy plane, the trace of the first paraboloid on the xy plane has the equation x squared plus y squared equals 4. This is the equation of the circle on the xy plane that is centered at the origin and with radius 2. On the xy plane, the solid is also bounded by a curve that is part of the trace of the second paraboloid on the xy plane. With z equals 0 on the xy plane, the equation of this trace is x squared plus the square of y minus 3 is 4. The projection of the solid onto the xy plane is the intersection of the interiors of the two circular traces. Here we get a good look at the solid. We are going to exploit the symmetry of the solid and its projection on the xy plane to set up double integrals for the solid's volume. We set up the volume integrals using two different elements of area. The first element of area is dx dy, where we integrate with respect to x first, then integrate with respect to y. Then we reverse the order of integration so that we use the element of area dy dx. For both orders of integration, we need to set up precise inequalities for x and y in order to determine the limits of integration. Assuming that the plane y equals 1.5 bisects the solid and its xy projection, we set up the volume double integral for the volume of the solid over the upper half of its xy projection. Then we multiply the result by 2 to get the solid's full volume. For the element of area dx dy, keep in mind that x is the first variable of integration, and so we traverse the xy projection in the x direction. We determine on what curve the projection begins and on what curve the projection ends. The projection's left boundary is the left half of the arc on the circle x squared plus y squared equals 4. Its right boundary is the right half of the arc. On both halves of the arc, we need to solve for x in terms of y because, let us repeat, x is the first variable of integration. On the left boundary, x equals minus the square root of 4 minus y squared. And on the right half of the arc, x equals the square root of 4 minus y squared. These give us the inequalities and the limits of integration for x. To determine the limits of integration for y being the last variable of integration, we find the minimum and maximum values of y within the projection's upper half. The minimum value of y is on the line y equals 1.5. And the maximum value of y is at the y-intercept of the bounding arc of the projection. Y is 2 at this y-intercept. We can now write the first double integral for the volume of the solid. Since we are using only the upper half of the projection, we start by multiplying everything by 2. The outer integral, and it is for the variable y, goes from 1.5 to 2. Then we write the inner integral, which is for x, the first variable of integration. Its limits of integration are minus the square root of 4 minus y squared and the square root of 4 minus y squared. The integrand is the formulation for z for the upper bounding surface, which is the first paraboloid. And so the integrand is 4 minus x squared minus y squared. Just as an exercise, if we do not assume the symmetry of the solid and its projection, we will have to set up separately the volume of the other half of the solid, the portion that is above the lower half of its xy projection. Following the x direction on the lower half of the xy projection, the lower half extends from the left half of the lower arc to the arc's right half. On the left half, x equals minus the square root of 4 minus the square of y minus 3. And on the right half, x equals the square root of 4 minus the square of y minus 3. Therefore, minus the square root of 4 minus the square of y minus 3 is less than or equal to x, which is less than or equal to the square root of 4 minus the square of y minus 3. The minimum value of y is at this y-intercept where y equals 1. The maximum value of y is on the line y equals 1.5. These inequalities give us the limits of integration for the double integral for the volume over the lower half of the solid's xy projection. And so we can also write the volume of the solid in the following way. We write the integral from 1.5 to 2. Then we write the integral from minus the square root of 4 minus y squared to the square root of 4 minus y squared of 4 minus x squared minus y squared. This is for the volume of the portion above the upper half of the xy projection. Then we add the volume double integral corresponding to the inequalities we had just found for the portion of the solid above the lower half of the xy projection. The outer integral is from 1 to 1.5. The inner integral is from minus the square root of 4 minus the square of y minus 3 to the square root of 4 minus the square of y minus 3. The integrand is 4 minus x squared minus the square of y minus 3, which is the z formulation for the second paraboloid, since the second paraboloid is now the upper bounding surface for this portion of the solid. Now we reverse the order of integration and use the element of area dy dx. We again assume the symmetry of the solid across the plane y equals 1.5. Since y is now the first variable of integration, we follow the y direction on the upper half of the solid's xy projection. The lower bounding curve is the line segment at y equals 1.5. The upper bounding curve is an arc on the circle x squared plus y squared equals 4. So that y equals the square root of 4 minus x squared on this arc. So we have 1.5 is less than or equal to y is less than or equal to the square root of 4 minus x squared. For the variable x, which is the last variable of integration, the minimum and maximum values of x occur at the intersection points between the upper bounding arc and the line y equals 1.5. And one can check that x equals plus or minus the square root of 7 divided by 2 at these points. And we have the limits of integration for x. To write the volume double integral for dy dx, if we assume the symmetry of the solid, we start by writing 2 times the integral from minus the square root of 7 divided by 2 to the square root of 7 divided by 2 for the variable x. Then we write the integral from 1.5 to the square root of 4 minus x squared. The integrand is 4 minus x squared minus y squared. If we do not assume the symmetry of the solid, we can start by writing the integral from minus the square root of 7 divided by 2 to the square root of 7 divided by 2, and then the integral from 1.5 to the square root of 4 minus x squared. The integrand is 4 minus x squared minus y squared. This is just the half of the volume of the solid. We still have to add the double integral for the volume of the portion of the solid above the lower half of the xy projection. We leave it as an exercise for the viewer to check that this volume equals the integral from minus the square root of 7 divided by 2 to the square root of 7 divided by 2, and then the integral from 3 minus the square root of 4 minus x squared to 1.5. The integrand is 4 minus x squared minus the square of y minus 3. As a further exercise for the viewer can carry out the integration whether by hand or by using a calculator or computer software, and check that the volume is equal to this value. Up to 3 significant digits, this is equal to 1.31.